Okay, good morning, Chase. We're gonna start off with differentiation of products and quotients. It's on page 6-15. Now here they show you a very simple method. I'm not going to spend too much time on it all. And the basic idea is, sorry, let me just get a pen here. Okay, what is going on? There we go. Okay, so on page 615, I thought it was the product and quotient rule, but it's not. Basically what they're saying is if you were to find the derivative of something like, okay, so basically what they are asking you is find the derivative of this function, and the method that they teach you is just, you don't have to use the product rule here. You can just multiply out these two brackets and then get this function and differentiate it using the normal, what do you call it, the polynomial formula for differentiation. So yeah, that's page 615. I'm not going to spend too much time there. You can just multiply everything out and you'll be fine. Okay, then they've got a whole bunch of exercises. Just note this is exercise 6.6, let's say number 12. They say find the gradient of the curve at the given point. Okay, now in order to do this, what are you going to do? Well, they give you the function y equals x squared minus, x cubed minus 1 at x equals 1. So you need to find the gradient at this point. So the gradient is the derivative, so m equals dy by dx, which is also equal to f prime of x, and we differentiate it using the rules we were taught yesterday. That gives 3x squared. Okay, so therefore f prime of x at 1, at x equals 1, so f prime of 1 equals 3. We just substituted 1 into our expression. So the gradient at x equals 1 is 3. Right. Okay, now here they talk about, now we're on page 618. The other pages were just exercises, so you can go do those in your own time. Okay, page 618, they say variables can be represented like, you can have multiple variables in an equation. For example, if I said, it doesn't have to be y equals x plus 5, it could be written as u equals v plus 5, something like that. And you could also have multiple variables in an equation. So let's just check here what they're showing. Okay, so for example, if your function is written like this, x squared plus y squared equals 7, and they say differentiate with respect to y. That means you're going to be wanting to take d by dy, okay? Which means that y must be on the right hand side. So you're going to write x squared equals 7 minus y squared. Well, let's just make this x. Let's take away the squared for now. And then we're going to say dx by dy because this is the variable we're differentiating with respect to, and they said differentiate with respect to y. So we have dx by dy equals negative 2y. Okay? Similarly, like if you had 2u plus 6v equals 1, and they say differentiate with respect to u, then we must have u on our, we put u on our right hand side, so we have 6v equals 1 minus 2u, v equals 1 over 6 minus 1 over 3 u, and then dv by du, u is at the bottom because we're differentiating with respect to u, equals minus 1 over 3. Okay, because, for example, the derivative of 2x, remember the rule, we take down the power, which is a hidden 1 there, take down the power and then decrease this power by 1. So the d by dx of that is equal to, multiply in front, so that is 2, put the x, and then decrease this power, 2x to the 0. And x to the 0 is 1, so it's 2 times 1 equals 2. So that's just how I differentiate it here. Just using that same polynomial rule that I gave you yesterday. Okay. Next is chapter 6.6. Let's move on, get some different space here. Okay, chapter 6.6 is differentiation of trig functions. Okay, and the first thing they do is they give you the proof on page 619. Don't even worry about that proof. It is completely unnecessary for your purposes. So all you need to know, and you know these are given in your formula sheet, but so f of x, so it's just the table f of x and f prime of x. So you have the function and its derivative. So if we've got y equals sine x, then we've got dy by dx equals cos x. And as I said, these are given, you just need to know how to use them. But it's useful to know it off the top of your head because, you know, if you know it off the top of your head, you can work much faster. Okay, so then they give you, they also give you the table with the additional trig functions, the ones you very seldom actually use. So these are the important 3. They do give the others, and I think it's also in your formula sheet, but these are less important, but I'm just going to write them down. So if y equals cosec x, dy by dx is equal to negative cosec x cot x. Okay, then we've got if y equals sec x, the derivative of that is sec x tan x. And if y equals cot x, dy by dx is equal to negative cosec squared x. Okay, these are less important, but they are in your formula sheet. As I said, you just need to know how to use them. So how are we going to use them? Well, they give you example 19, so let's take a look at that one. example 19. And this is quite nice because what they've done is, well, let me first write down. They've basically say differentiate y equals 4 sine x minus 2 cos x plus x squared. Now, our formulas show how to differentiate sine, cos, and tan. They say nothing about if there's a coefficient like we have here. We've got the 4 and the 2. So I just want to point out another rule to you, and that rule is that d by dx of a constant times f of x is equal to a constant times d by dx of f of x. So basically what this is saying is that if you've got a constant in front of your f of x, which in this case here is sine, so here's f of x and here is c. So basically what it's saying is you can just take this constant out in front of your derivative. So the derivative of 4 sine x, we can take that constant out. So it's 4 times the derivative of sine x. Okay. Easy stuff. So that's what that says. And remember here, we're also going to be using the, I'm going to call it the sum property, which is d by dx of f of x plus g of x equals d by dx of f of x plus d by dx of g of x. So what that says is we can differentiate each term individually and then just add up the results. Okay, so now let's look at our function that we need to differentiate. It's got a sine, a cos, and an x squared. So what do we actually have here? We've got a trig, and polynomial. So, and we've also got constants in front, so we're going to be using this rule here. And, you can differentiate each term individually. So, let's quickly do our differentiation. Y, so dy by dx is equal to, so let's differentiate each term, okay? 4 sine x is equal to 4 times dy by dx of sine x. And we know from the rules that I gave you, so whenever you're doing a trig, whenever you're doing differentiation, when you see a sine x or whatever, look at your table and see if you can't find one that exactly matches. Because here we've got sine x, the derivative is cos x, so it's an easy differential. So that is 4 cos x. So we've differentiated our first term. The next one is minus 2. Okay, derivative of cos x is minus sine x. So we get a plus there, and because minus 2 times minus gives us a plus. So plus 2 sine x. And then we've got our polynomial. And how do we differentiate that? We take the power down to the front, so it gives 2. Then we write down our x. Then we reduce our power by 1, so 2x to the 1. And there you go. So our derivative is 4 cos x plus 2 sine x plus 2x. And there you go, you've done your derivative. So, yeah, that was quite a nice little example. And next your book goes on. Your book is actually quite nice in this section, I must say. It really guides you through the process nicely. So if you sit and work through this a little bit, doing the examples along the way, it's going to work out really nicely for you. Like, you should be able to understand it very nicely. Okay. Okay, so there we've got our derivative, and let's take a look. In example 21, they tell you that, so in example 21, they tell you that difficult functions must be simplified using identities. Difficult functions must be solved using identities. Something like tan squared a minus 4 over tan a plus 2. And they say you need to, before you can differentiate this, you need to simplify it using identities. That might be the case, and in some cases that's better. You could also just use the quotient rule, which I'm sure we'll get to later. Okay. Okay. Next we've got differentiation of e to the x, which is section 6.6. Section 6.6 is differentiation of e to the x. Okay? And if the function y equals e to the x, dy by dx is also equal to e to the x. Okay? So that's simple. E to the x stays e to the x when you derive it. So if you had 2e to the x, the derivative would be 2e to the x. Okay. Section 6.7 is differentiation of log base e and a to the x. Okay. So, by the way, for 6.6 they also go through this whole proof. You don't need to know the proof, you just need to know this piece. You just need to know that. And even that is given in your formula sheet. Okay, differentiation of log base e of x and a to the x. So basically they go through this whole proof just to show you that, and once again, the proof is not important. If y equals log e of x, log base e of x, dy by dx is equal to 1 over x. Okay? And for the function y equals a to the x, dy by dx equals a to the x log a with base e. Okay. Now they talk about log base e of x. That is also sometimes just written as ln of x, ln of x. Just so you know, it's a bit easier to write ln of x than log base e. I much prefer writing ln of x, but I suppose that's really up to you. Okay, so they give a couple of examples on page 626. Okay, and to be perfectly honest, I think some of them are a little bit unfair to be asking, given that you don't know all of the rules of differentiation yet. So I think it's quite stupid, those examples, personally. You can try them and see if you can get them, but they don't make sense given what you know. Like, there's no point in asking you that. So yeah, let's just keep on. Okay, so here on page 627 they give you a summary of all of the trig rules. Okay, or all of the trig, trig. They give you a summary of all of your derivatives, which is quite nice. So they give you the table that'll be given to you in your exam, and it's basically for the functions y equals ax to the n, y equals e to the x, y equals ln x, y equals a to the x, and then all the trig functions, y equals sin x, cos x, tan x, cot x, cosec x, and sec x. They give you all the derivative rules for that. So there's a nice summary there on page 627. Okay. Now, then we move on to section 6.9. And this is where we start to learn all of the rules. Okay. So they start off with the product rule. And once you've mastered all of these rules and you know how to use the table of derivatives, then you'll be able to do pretty much any derivative imaginable. Okay. And basically, the product rule says that, you know, what if I've got two functions, something like y equals root x x squared plus 1, right? So let's call this one f of x, and we can call this one g of x, right? So I could very easily differentiate f of x because it is x to the 1 over 2, and I can just differentiate that. It becomes 1/2 x to the minus a half. And if I wanted to differentiate g of x, I would get very easily 2x, and that would be it. Okay? But what if I want to differentiate these two? Like, this is not one of the basic functions that pops up in our table of derivatives. So how do we differentiate it? We use the product rule. So what the product rule says is basically, I've got one function, like this. I've got one function that exists in my trig table, multiplied by my derivative table, multiplied by another function, which can be done just using my derivative table. And I need a formula for what the derivative is after that. Okay? So, okay. I see that your book doesn't call it f and g. They're going to call the functions u and v. Okay, whatever, same thing. U and v. I'll stick to their notation. Basically, the product rule states that if y equals uv, i.e. if the function is the product of two smaller functions, so here, see, two functions, so if it can be broken up into the product of two functions, then the derivative is equal to u du hang on, du by dx times v plus dv by dx times u. Okay? Yes. Okay. Then on page, so that is stated there. That goes in purple because this is one of our rules, and this is the product rule. So dy by dx for the product rule, where you've got functions u and v, is du by dxv plus dv by dxu. You could also write it dv by dxu plus du by dxv. Doesn't matter, but that's how I prefer to write it. On page 628, they give the proof of the product rule. You don't need to know it, so personally I wouldn't even read it, just skip over it completely. And let's take a look at an example. Let me just erase, actually. Let's erase this so that I've got a bit of space and I can get some work here with the rules still on the screen. Okay. So, I'm going to do both of the examples, I think. So, we've got example 30. So, it says differentiate y equals root x into x squared plus 1, right? So let's see, you've got a product of two polynomial functions. So let's call this u, let's call this v, right? And then we know, okay, so they're asking you to derive, right? So we know that dy by dx is equal to du by dxv plus dv by dxu. So what do we need? We need du by dx, we need v, we need dv by dx, and we need u. We already know the values of u and v. We need to calculate du by dx and dv by dx and then substitute it into this formula. So du by dx equals d by dx of root x. So the derivative of root x equals d by dx of x to the half. And this is a polynomial, so what do? We take the 1/2 to the front, 1/2, write down our x and decrease this power by 1, so minus a half. Okay, and then dv by dx equals d by dx of x squared plus 1. This is also a polynomial function. What do? Take the 2 down to the front, 2, write down our x, reduce the power by 1, and the derivative of a constant is 0, so it's 2x. So now that we've got those two values, we can write down that now dy by dx is equal to du by dxv plus dv by dxu, because we know this is a product rule, so we're using the product rule formula, dv by dxu, and then we just substitute in, because we've got, let's do colors, we've got du by dx, it's over here, we've got dv by dx, it's over there, and we've got u, and we've got v. So we can just substitute the values in, multiply out, and we'll be done. So, okay, du by dx is 1/2 to the negative a half, so 1/2 to the 1/2 x to the negative a half, times v, which is x squared plus 1, plus dv by dx is 2x, there it is, times u is x to the half, or root x. Okay, so now we can multiply this out and we'll have our derivative. So this is equal to 1/2. If we multiply that, we get x to the 3/2 plus 1/2 x to the negative a half, plus, then we multiply these and we get 2x to the 3/2. And there you go. Let's just double check our answer. Okay, they wrote theirs quite differently from me. Let's double check here. Okay, they just simplified further because we've got both of these are x to the 3/2 terms, so we can add them, which leaves us with what's that? 5/4 x to the 3/2 plus 1/2 x to the negative a half. Yeah. And this could also be written as 5/4 x to the 3/2 plus 1/2 x to the negative a half is 1 over root x. Okay, you could leave it like that or like that, but there you go, you found your derivative. Okay, next we're going to do example 31. Okay, and it says differentiate y equals x squared sine x. Okay, so can you see once again we've got two functions because we know x squared is a polynomial and sine x is a trig function. So there we've got our u and our v. So we've got two functions multiplied, so we're going to use the product rule. Okay, and what is the product rule? The product rule is dy by dx of a function uv or vu is equal to and then we've got du by dx times v plus dv by dx times u. Okay, so once again, what do we need? We've got we need to calculate du by dx and dv by dx. So du by dx equals d by dx of x squared, which is take the 2 down in front, write the x, reduce the power by 1, and let's do dv by dx, which is equal to d by dx of sine x. And if you look directly at your table, your derivative table, you'll see the derivative of sine x is cos x. Okay, now we can just substitute into our formula. So you should actually rewrite this formula over here, but I'm not going to. So now we've got dy by dx is equal to du by dx is 2x times v, which is sine x, plus dv by dx is cos x, dv by dx cos x, times u, which is x squared. Okay, so we multiply it out and we've got 2x sine x plus x squared cos x. And there you go. There you found your derivative using the product rule. I see they took out a common factor x, but who cares? There we go. X squared cos x sine x times 2x. Yeah, and that is the correct answer. Example 32 is a bit ridiculous. They basically, in example 32, they give you 3 brackets. They say y equals, and they give you a bracket with each with 2 terms in, and they say find the derivative. And they did it by using the product rule, which makes it really long. Personally, I would recommend rather just multiply it out. So you've got a term here, term there, term. If you apply FOIL to these 2 brackets, you end up with a 3-term bracket. 1, 2, 3. Okay. Then you've got a 2-term bracket here. And I assume you know how to multiply this out, but basically you would multiply this term by each of them and add, and then you multiply this term by each of them, and then just take the derivative because it's just a normal polynomial. But that's just a bit of a ridiculous example if you ask me, so I wouldn't stress about it too much. Okay, let's move on to the next rule, which is the quotient rule. Do I want to save my picture? No. Okay, so we're going to do the quotient rule next. It's another important rule. Basically, there's this huge big proof. Once again, you don't need to know it, so I'm not even going to bother and waste your time with it. Let's be real. So that proof that's on page 631, don't bother with it. You don't need it. What you just need to know is that if a function y equals u over v, so this is the quotient rule, section 6.10. Okay, if a function y equals u over v, where u and v are functions of x, functions of x, okay, then dy by dx equals v du by dx. So v du by dx, u dv by dx over v squared. Okay, and that is your quotient rule. So basically, if you see a function which can be broken up into a function over a function, and then you can apply your quotient rule to get the derivative. So a nice example, I'm going to give two nice ones in your book. So let's just hit those quickly. So example 33 says if y equals 2x over x plus 1, okay, determine dy by dx. And you can see here, there's a polynomial function at the top and there's a polynomial function at the bottom, because you're not going to see this function in your table of derivatives, but you'll see this function in your table of derivatives and this one, because these are just both polynomials that you differentiate using the polynomial rule, which is the first one we did. Okay, so we'll call this one u, we'll call this one v, okay, and then once again the quotient rule. Quotient means function over function, or divide basically. So we can just do that quickly. So we've got u, we've got v. We need to calculate du by dx and dv by dx. So let's do it. Du by dx equals d by dx of 2x, which is equal to 2. Because we keep the 2, this is x to the 1, so you take the 1 in front and you reduce the power, it becomes 1x to the 0, and x to the 0 is just 1. And then let's do dv by dx. dv by dx equals d by dx of x plus 1. Okay, and we need to differentiate that. Once again, it's a polynomial, so you've got, this is x to the 1, so we take the 1 down in front, so 1x, then we reduce that power, so that becomes to the 0, and then plus 1, we take the derivative of that, it just becomes 0, because the derivative of a constant is 0. So, and x to the 0 here is 1, so the dv by dx is equal to 1. Okay. So now we've got du and dv. So now we can substitute into our formula. So we can say dy by dx equals v du by dx minus u dv by dx over v squared. Okay, and if we substitute our values in, we know what v is. V is x plus 1, x plus 1. Okay, du by dx is 2 minus u, now u is 2x, dv by dx is 1 over v squared, which is x plus 1 all squared, x plus 1 squared. Okay, so now we can just multiply it out and we've got a derivative. So this is 2x plus 2 minus 2x over x squared plus 2x plus 1. That is equal to, those two cancel, it gives 2 over x squared plus 2x plus 1. And there you go. There is your the derivative, your dy by dx, using the quotient rule. Fantastic. And then let's quickly do example 34. Example 34. Okay, and example 34 says, determine the derivative of the function y equals you know, this example is a little bit too basic. I want to do one that's a little bit more interesting. So let's do if y equals cos x over 2x squared. Okay? So once again, you can see it's a function over a function because it's a trig function over a polynomial function. So let's call this is u and this is v. So we just say, to write it out properly, which I haven't done yet, you need to say let u equal cos x, and we know we're using the quotient rule, so we know we need to calculate du by dx and dv by dx. Okay, I see your book is using prime notation in this example, so I'm going to do the same. Let u equal cos x, therefore u prime, which is the same as du by dx, is equal to negative sine x, and that just comes from your table of derivatives. And then we're going to say also let v equal 2x squared, therefore v prime equals, and this is a polynomial, so take the 2 down in front and multiply, that gives 4, write down your x and reduce your power by 1, so it just gives 4x. Okay, and then we use our quotient rule. So what's the formula for our quotient rule? Dy by dx equals u prime v minus v prime u over v squared. Okay, and now we can just substitute in. So we know that so we've got u prime, it's minus sine x, so we've got minus sine x, okay, times v, and v is 2x squared, then minus v prime is 4x, u is cos x, over v squared is 2x squared, and then we can just multiply out and we've got our derivative. So 2, that gives minus 2x squared sine x minus 4x cos x over 4x to the 4. And there you go, you've calculated your derivative. And that is the quotient rule. The next rule we've got is the chain rule. And then we move on to just a couple of little sections. So it's just a couple of little sections there's left to go. I think I'm going to do that in a video next week. And then we will be, I think, let's give it, how many weeks do we have to go until your exams? 2 weeks, maybe 3. Check on my calendar here quickly. Okay, so we are here. Your exam is on the 17th. So we've got 1 week, 2 weeks, no, is it that much? 1 week to the 5th, 2 weeks, 2.5 weeks essentially left to go. Okay, so I think I'm gonna try push it to 3 videos per week. So then we can finish differentiation. We'll do 2 videos. So we've got 6 videos left to go by my calculation. If we've got 6 videos, that's 3 a week for 2 weeks. 6 videos. I will do 2 more on differentiation. And then we're going to do 4 on integration, which will be a bit of a push, but I think we can just fly through integration and I'm sure you'll be fine. So yeah, thanks for watching. Cheers.